In this tutorial we will cover chapter 10, graphs, and that will be the last topic that we will cover for the MT131 course. Let's start with the definition of a graph. Of course, we have seen examples of graphs when we studied relations. We were able to represent a relation using a directed graph. But the idea of a graph is more general. We will look at both directed graphs and undirected graphs. Starting with the definition of a graph is an ordered pair, V and E. It consists of V is a non-empty set of vertices or nodes, and E is a set of edges. To have a graph, you need at least one vertex. Now, each edge has either one or two vertices associated with it. Each edge will connect either two vertices or one vertex, and it will connect one vertex to itself. The vertices associated with the edge are called the endpoints. An edge is said to connect its endpoints. There's a remark here that the set of vertices might be infinite. A graph with infinite vertex set is called an infinite graph. طبعا يعني all the cases we'll look at will be finite graphs, meaning it will have a finite set of the vertex set is finite. Here is an example of a graph. This graph, the set of vertices has four vertices labeled A, B, C, D. The edges, each edge is defined by the two vertices it connects. For example, we will have AB, we'll have AC, BC, BD, and CD. The vertices are marked, labeled, and then the edges, each edge in this graph connects two separate vertices. But here are the two sets. That's what defines the graph, is the set of vertices and the set of edges. There are many models that use graphs. These are just examples. Computer network, for example, we will look at several examples of computer networks that use graphs to represent the network. You can also we will look at social networks like this graph here on the slide, communication networks, information networks, software design, transportation network, biological networks. All of these are examples of models that you can use a graph to represent. The picture of this graph is a friendship graph where two people are connected if they are Facebook friends. For the nodes here, the vertices represent people. There's an edge between two vertices if the two people are Facebook friends. This is an example of a social network. The next few graphs are from the book, from the textbook. They are for networked, graphs that represent computer networks. A computer network can be modeled using a graph where the vertices of the graph represent data centers. The edges represent communication link. In this computer network, the data centers are cities, named after the cities. For example, San Francisco, Los Angeles, Denver. Anytime there is a communication link between two centers, we draw an edge. Here is an example of a computer network. A simple graph, here's the definition for what a simple graph is. A graph in which each edge connects two different vertices and where no more than one edge connects the same pair of vertices. This is called a simple graph. The first condition that each edge connects two different vertices, that means there is no loops. There is no edge that connects the vertex to itself. A simple graph has no loops. The other condition that no more than one edge connects the same pair of vertices, That means you don't have any multiple edges. You cannot have a pair of vertices with more than one edge connecting them. Of course, the graph we started with was a simple graph because it had no loops and no multiple edges. Here is now, if a graph has multiple edges, it's called multigraph. Here is the same network, the same data centers. This time it's showing multiple links. Sometimes with big data centers there is a lot of traffic, so more than one data link is used. In this case, multiple edges might connect a pair of vertices. In this example, these are the same data centers. You notice there is 3 links between Denver and Chicago. There is 2 links between Los Angeles and Denver. It's possible to have only one link or even no links, but you are allowed to have multiple edges. This is called a multigraph. This is a computer network with multiple links between data centers. The next type of graph is called pseudographs, and here loops are allowed. So multiple edges are allowed and loops are allowed. This is the loop in this in this network. It's a link that connects a data center with itself. It is used for diagnostic purposes. A graph where loops are allowed and multiple edges are allowed is called a pseudograph. And this is now a computer network with diagnostic links. The other type of graph, which we should be familiar with because we use them to represent relations, are directed graphs. A directed graph or a diagraph, again, it consists of a pair V and E. The set of vertices V is non-empty. The difference now, the set of edges, these are now directed edges or arcs. Each directed edge is associated now with an ordered pair of vertices because it will start at a vertex and ends at another vertex. That's the difference now. Edges have directions. The directed edge associated with the ordered pair UV is set to start at U and ends at V. When a directed graph has no loops and has no multiple directed edges, it's called a simple directed graph. We're still working with the same computer network. This time the communication links are one-way links. Here is an example now of a directed graph. Notice that now these are not multiple edges. This is a simple directed graph. To have multiple directed edges, 2 edges must start and ends at the same they both must start at the same vertex and ends at the same vertex. This is an example of a simple directed graph. A directed multigraph now may allow for multiple directed edges, as we can see in this computer network. This is an example of a computer network with multiple one-way links. You may have more than one link starting at one vertex and ending at a second vertex. This is a directed multigraph. طبعا the usage of graphs in modeling, we have already seen examples of using graphs. What type of graph to use depends on the application. Whether, for example, whether the edges in the graph needs to be directed or not, whether multiple edges are needed, whether loops are needed. The type of graph is certainly depends on the application. This table, which is from the book, is a summary of the different graphs we considered so far. The first 3 are undirected. Simple graph is an undirected graph multiple edges are not allowed, and loops are not allowed. Multigraph is also undirected. Multiple edges are allowed, and loops are not allowed. The pseudograph is an undirected graph. Multiple edges are allowed, and loops are allowed. The next two are directed graph. A simple directed graph is a directed graph. Multiple edges are not allowed, loops are not allowed. A directed multigraph is a directed graph where multiple edges are allowed and loops are also allowed. The final type, which we will not study in this book, are called mixed graphs. That means some of the edges have directions and some of the edges do not have directions. We will not consider this type of graph. Next, we would like to consider some graph terminology, some terms that are used when we are studying graphs. For example, adjacent. If you have two vertices, you will say that the two vertices are adjacent. An edge, for example, connects two vertices. We'll talk about endpoints of an edge. The degree of a vertex. We'll talk about initial and terminal vertices. We will see how to, for directed graphs, we will see how to calculate the end degree, the odd degree, and then we will look at several types of graphs. For example, we will consider the complete graph, the complete bipartite. Cycles are types of graphs that we will consider. Wheels and N-cubes. These are different types of graphs that we will cover, and we will show examples of each type. Here is some of the terminology used in some examples. We'll start with an undirected graph. G is an undirected graph. E is an edge. E is associated with an unordered pair of vertices. So here is some of the things we may use. We say vertices U and V are adjacent. That is because there is an edge connecting them. So U and V are adjacent, or we can say they are neighbors, or that U and V are connected. Now the edge E, since it connects U and V, it is incident with U, meaning it touches U, and also incident with V. The edge E connects U and V. U and V are the endpoints of the edge E. All of these terminology can be used when we're working with an undirected graph, dealing with edges and vertices. We will see those terms used a lot. Now we would like to talk about the degree of a graph, the degree of a vertex, starting with an undirected graph. G again is an undirected graph. V is a vertex. The degree of V, and we write it, use DEG of V. This is short for degree of V, is the number of incident edges. If you happen to have a loop, the loop is counted twice. Think of it as touching the vertex twice. A loop is counted twice. But this is what the degree of a vertex is, the number of incident edges. And if you have a loop, you count it as twice. It will contribute 2 to the vertex degree. If a vertex has degree 0, that means it's not incident with any edge, so we call it isolated. There's also a special term for a vertex of degree 1. It's called dependent. That means it's incident with one edge only. We call it appendant. We have some formulas that deals with the degree of a graph. G again is a graph with vertex set V, and E is a set of edges. This could be, it is undirected. It could be simple, it could be multigraph, or it could be a pseudograph. The number of edges is E. So what the handshaking theorem tells me is that the sum of all degrees of all vertices in the graph is equal to 2 times the number of edges in the graph. If you add up all the degrees of all the vertices of the graph, that number will be twice as much as the number of edges. For one thing, the sum of degrees will always be even, and this is one way, if you know the sum of the degrees, you can find the number of edges. Certainly if you know the number of edges, then you will know the sum of the degrees. So we will look at examples how to use the handshaking theorem. Here's some examples. How many edges are there in a graph with 10 vertices, each of degree 6? Well, you have 10 vertices, each of degree 6, so the total degrees is 6 times 10, which is 60. This is twice as the number of edges, but the number of edges is 60 divided by 2, or 30. This graph will have 30 edges. Here is another example. If a graph has 5 vertices, can each vertex have degree 3? The answer is no. Then if you have 5 vertices, each have degree 3, then the total degrees is equal to 5 times 3, or 15. And that's an odd number. And by the handshaking theorem, we know the sum of degrees must be even. For this, it's not possible to have a graph that has 5 vertices, each have degree 3. Let's look at an example of verifying the handshaking theorem. We will calculate the degree of each vertex and add the sum of all degrees. That should equal to twice as much as the number of edges. With A, you can count 1, 2, 3, 4, and the loop counts as 2. There's 6 edges, the degree of A must be 6. For B, there is 4 edges that are incident with B. The degree is 4. The degree for C is 1. There's only 1 edge incident with C. D is isolated, but the degree is 0. The degree of E is 3. The degree of F is 4. The degree of G is 2. If you add the sum of all degrees, 10, 11, 14, 18, 20. If the sum of the degrees is 20, then the number of edges is 20 divided by 2, which is 10. And if you count the edges in this graph, you will find that it has 10 edges. For directed graphs, we will talk about what it means for 2 vertices to be adjacent. With a directed graph, edges have direction. For here, we will take G to be a directed graph. It could be a multi-directed graph. E is an edge in G with UV here now is an ordered pair. This is U is the beginning of the edge, and V is the end of the edge. So here is some of the terminology we use for directed graph. U is adjacent to V. V is adjacent from U. The edge E, the directed edge E, comes from U and goes to V. E connects U to V, or E goes from U to V. The terminology that we will use a lot is that the initial vertex of this edge, E is the directed edge, the initial vertex is U, the terminal vertex is V. Now we would like to define the in degree and out degree, and then the degree in the case of a directed graph. In a directed graph, we count the edges going to the vertex, where the vertex is a terminal vertex, and also we count the edges that start at the vertex, where the vertex is initial. But these are the in degree and out degree. Starting with the in degree of V, the in degree, and we use the same terminology DEG, but with a minus sign. This is read the in degree of V is the number of edges going to V, where V is terminal. The out degree, which we use the same terminology, DEG, with a plus sign. This is read the out degree of V is the number of edges coming from V, where V is an initial vertex. The degree of a vertex is just the sum of in degree and out degree of the vertex. A loop, what about a loop? A loop طبعا starts and ends at the same vertex, فit will add 1 to the out degree and will add 1 to the in degree. The handshaking theorem for directed graphs. Again, G is a directed graph, possibly a multigraph. V is the vertex set, and E is the edges. What the handshaking theorem says for directed graphs, and the sum of in degrees of all vertices is equal to the sum of out degrees for all vertices. This is half of the total degrees, which is equal to the number of edges. For example, if the sum of the out degrees is 10, then the sum of the in degrees is also 10. And that makes the sum of all degrees is equal to 20. Half of that is the number of edges. We will look at an example to verify this for directed graphs. There is a note here that the degree of a node is unchanged by whether we consider its edges to be directed or undirected. لأن if we consider it to be directed, we're counting the number of edges going out and the number of edges going in. If we remove the direction, the same vertex is still incident with the same number of edges. For the degree of a node is not changed whether we consider the edges to be directed or undirected. Here is an example of the handshaking theorem for directed graphs. You can calculate the out degree for each vertex and the in degree and check to see if the sum is equal. For at least some of the vertices, for A for example, there's 3 edges starting from A, where the out degree is 3 for A. For B it is 3 also, because there's 3 edges starting at B. You can count the out degree for each vertex, count the in degree for each vertex. If you add them, the sum in each case will be 10. طبعا this is the sum of the out degrees is equal to the sum of the in degrees, which is equal to the number of edges in the graph, which is 10. Next, we would like to look at special graph structures. And here is the types that we'll look at. We'll look at complete graphs, which is Kn, complete bipartite graphs, which is Kmn. We'll look at cycles, which is Cn, wheels, which is Wn, and finally n cubes, which is Qn. طبعا these are special types of undirected graphs. Let's start with the complete graphs. N here is a positive integer. A complete graph on n vertices, which we use Kn, is a simple graph, so there's no loops and there's no multiple edges. It will have n vertices. Each vertex is adjacent to every other vertex. Every possible edge that you can draw is there. Every vertex is adjacent to every other vertex. If you want to use logical statement to describe a complete graph, for all u and v in the vertex set, if u is different than v, then the edge uv will be in the edge set. طبعا the shape of the graph will depend on how many vertices it has. K1 has only one vertex, no edges. K2 has 2 vertices and 1 edge. K3 is this triangular shape. K3 has 3 vertices and 3 edges. K4 has 4 vertices and 1, 2, 3, 4, 6 edges. طبعا the way to count the number of edges, there's a formula to do this. Kn has n vertices and n times n minus 1 divided by 2. This formula gives you the number of edges. طبعا احنا we looked, for example, K4 will have 4 vertices and how many edges? 4 times 3 divided by 2, which is 6 edges. But this is a formula that's useful if you need to know the number of edges in the complete graph on n vertices. The next type of graph is called complete bipartite graphs. A bipartite graph is a graph where you can divide the vertex sets into 2 groups, and all the edges in the graph connects a vertex from one group to a vertex in the second group. There is no edges connecting the vertices in any of the groups. All the edges connect a vertex from one group to the other group. طبعا the 2 numbers k, m, n refers to m is the number of vertices in the first group and n is the number of vertices in the second group, and k طبعا is for complete. Every vertex in the first group is connected to every vertex in the second group. Here is an example of the graph to the left, K23. طبعا 2, 3 refers to the first group, which is on top, has 2 vertices. 3 is the group in the lower part. There is 3 vertices. Every vertex from the first group is connected to every vertex from the second group. In fact, the number of vertices طبعا will be just the sum of these 2 numbers. For k, m, n has m plus n vertices, and the sum of these 2 numbers will give me the number of vertices. The product will give me the number of edges. For K23 will have 5 vertices and 2 times 3, which is 6 edges. The picture to the right is a picture of K35. Here طبعا the top group, the group of vertices on top, has 3 vertices. The group in the lower part has 5 vertices. Every vertex from the first group is connected to every vertex in the second group. The number of vertices in K35 will be 8. The number of edges is 3 times 5, which is 15 edges. The next type of graph, special graphs, is called a cycle. And a cycle, طبعا, to have a cycle you need at least 3 vertices. For n is larger than or equal to 3. A cycle then is again it is a simple graph where you can list the vertices, and you have a sequence of vertices v1, v2 up to vn. Now every vertex is connected to the next vertex. v1 is connected to v2, v2 is connected to v3, and the last vertex vn is connected to the first. The edges go on a cycle. The examples will clarify what a cycle is. The smallest cycle is C3. There is 3 vertices, and you have this triangular shape. C3 is the same graph as K3, the complete graph on 3 vertices. C4 has 4 vertices and 4 edges. C5 has 5 vertices and 5 edges. طبعا you can see why it's called a circle. You can start at one of the vertices and go through each vertex and come back to the same vertex. Should also be clear that Cn has n vertices and n edges. The number of vertices equal to the number of edges. For C8 will have 8 vertices and 8 edges. The next type of graph is called a wheel. And again, a wheel you need at least 3 vertices. N is greater than or larger than 3. Equal or larger than 3. For a wheel Wn is a simple graph. And it is obtained by taking a cycle Cn. Start with Cn and add one vertex, one extra vertex, you call it the hub. and add n extra edges, and you connect the hub to each existing vertex. The resulting graph is called the wheel, WN. You can do it by construction. Again, WN, you start with CN, cycle on n vertices, add a vertex, call it the hub, and connect the hub to each existing vertex. The resulting graph is called the wheel on n vertices. Here is W3, the smallest wheel. You can see that we started with C3. We added a vertex in the middle and connected it to each edge, to each vertex. This resulting graph is W3. W4 should also be clear. This is that we started with C4. We added the vertex in the middle, and which we call the hub, and connected the hub to each vertex in the graph. You can do this to every wheel. It starts with a cycle and with a vertex added and with edges connected to each existing vertex. The Wn will have n plus 1 vertices. Then you started with Cn, you started with n vertices and added a vertex. For the number of vertices in Wn is n plus 1. And the number of edges is doubled. Now we started with n edges and we doubled the edges. The number of edges is equal to 2n. For example, W8 will have 9 vertices and 16 edges. The next graph is called N-cube or Hypercube, and again it's done by construction. We're starting with n, a positive integer. Hypercube Qn is a simple graph consisting of 2 copies of Qn minus 1. You have to start with the first copy of Qn, and then the next copy is just take 2 copies of the previous graph and connect the corresponding nodes. Start with Q0 is just simply is a vertex, one vertex and no edges. This is Q0. By definition, then Q1 will be 2 copies of Q0 with the 2 vertices connected. Q2 is 2 copies of Q1 with the corresponding vertices connected, so you get the square. Q3 is 2 copies of Q2 with the corners connected, so you have this cube. Q4 may be hard to see, but this actually is made up of 2 cubes, 2 copies of Q3 with the corners. There's 8 corners connected. So the result is Q4. Beyond n equal 4, the graph becomes complicated. Qn will have 2 to the n vertices, that's the number of vertices, and n times 2 to the n minus 1 edges. Next, we would like to discuss graph representations. A graph can be represented using an adjacency list or an adjacency matrix or an incidence matrix. We will look at examples of the 3 different ways to represent a graph. We will do this for both directed and undirected graphs. Starting with an adjacency list, it's just a table. Here is an example of a graph. It's a simple table that has 2 columns. The first column you list the vertices of the graph. In the second column to the right, you list all the adjacent vertices. For example, A is adjacent to B and C. Next to A we list B and C. B is adjacent to A, C, E, and F, so we just list them to the right. For every vertex, in the left column, list all the vertices that's adjacent to that vertex, all the vertices that have an edge connecting it to that vertex. If you notice D, for example, D is an isolated vertex, but there's nothing adjacent to it, so you just leave it blank. This is called an adjacency list. The other way to do this is using an adjacency matrix, and this one the idea should be familiar now. But here is a graph. For what you want to do is list all the vertices in one row above the matrix and list them again in a column, and anytime there is a vertex from the column connected to a vertex in the row, then use 1 for true. And if there is an edge, record 1. If there is no edge, then record 0. طبعا for this graph you notice that there is no loops, there is no vertex that's connected to itself, but the diagonal here will be all zeros. The other thing that should be clear also in this matrix will be a square matrix, because the number of rows is equal to the number of columns. The third important thing is that this matrix will be symmetric. Then, for example, if B is connected to A, then A is connected to B. So anytime there is one, any entry of 1, then across the diagonal you will also have 1. But this graph will be symmetric. Let's look at least some of the vertices. For example, A is incident, or there is an edge from A to B and from A to C. For A with B, list 1, and A with C is 1. Each one here represents an edge of A with another vertex. A with B is 1, A with C is 1. The remaining entries is 0. For B, for example, B is incident to A, C, and E. For B with A, 1, B with C is 1, B with E is 1. The remaining entries is 0. Look at the isolated vertex, D. طبعا the row for D will be all zeros because it's not incident with any other vertex. For these, the resulting matrix now is called the adjacency matrix for the graph that we started with. طبعا you can, if you have the matrix for the graph, you can reconstruct the graph, doing the reverse process. For example, here's an example. We want to draw the graph using the following adjacency matrix. Assuming you start with this matrix and that this is a matrix for a graph, then you need to specify the vertices. This is a 4x4 matrix, so it represents a graph that has 4 vertices. Here is the labels A, B, C, D. Now you start by drawing the labels A, B, C, D, and go back to the matrix. Wherever you see 1, anytime you see an entry of 1 between 2 vertices, then they are connected. If you see 0, then they're not connected. For example, A is connected with itself. There is a loop at A. A is connected with B, so I draw an edge with B. A is also connected to C. طبعا A is not connected to D, so I don't draw an edge between A and D. You just go to every pair of vertices, one from the row and one from the column. If there is one in the matrix, that corresponds to an edge, so you draw that edge. طبعا the resulting graph will be a graph, and that graph has the matrix that I started with as the matrix that represents that graph. Then every graph you can represent it using a matrix, a square matrix, and every square matrix can be a matrix for a given graph, طبعا for a given set of vertices. Now with simple graphs, you end up with either 1s or 0s, and 2 vertices are either connected or not. You end up with a 0 and 1 matrix. But now an adjacency matrix for a multigraph, the entries may be more than 1, they could be different than 1 or 0s. Then for a multigraph, the entries in the matrix are the number of edges connecting the 2 vertices. Here is an example of a multigraph. For example, if you look at طبعا A is not connected to itself, so it's 0. Let's look at A and B. There is 3 edges connecting A and B. The first row, second column has the entry 3. طبعا the same for the entry 3 1. 2 1 also has 3. لأن that's the number of edges between A and B. Look at, for example, A and D. There is 2 edges. The entry in the first row and fourth column is 2, and there's 2 edges. In this case طبعا the entry for any 2 vertices, the entry that you record is the number of edges between them. You will get the resulting matrix will be a square matrix. It will be symmetric, but طبعا it will have entries other than 0s and 1. This is now an example of a matrix that represent a multigraph. Okay, let A be this is now another example. This is another thing we can do with matrices, is that you can tell the degree. And if you have the matrix for a graph, then you can tell the degrees of each vertex from the matrix. For example, if this is a matrix on the graph that has A, B, C, D as labels, then for example, the first row represent the vertex A. Each one here represent an edge that's incident with A. So if I add the entries of the row, that will give me the degree of A. طبعا you can do the same with a column. The sum of entries of a column also gives you the degree of that vertex. For this matrix then, طبعا imagine A, B, C, D written in the correct order. The degrees of those vertices are the sum of each row. The degrees will be 3 for A, 2 for B, 2 for C, and 1 for D. This is just adding the entries from the row. You can tell the degrees of each vertex. Now for directed adjacency list, طبعا your adjacency list, the first column you list the initial vertex. Here in this graph you have V1, V2, V3, V4, and V5. And in the second column you list the terminal vertex. Starting with V1, you have a directed edge starting from V1 going to V2, also V4 and V5. You list V2, V4, V5 in the terminal vertex. For example, V2, there's only one edge starting at V2 and it's going to V4. V4 is the terminal vertex in this case. V3, there's only one edge starting at V3 and it ends at V5, but the terminal vertex is V5. V4, there is no edge starts at V4, you leave the space blank, and there is no terminal vertex here. Finally, V5, there's only one vertex, one edge starting at V5, and it ends, the terminal vertex is V2. List V2 in the second column. But this is now the adjacency list for a directed graph. The first column you list the initial vertex, and for each vertex, the second column you list the terminal vertices. Here is now an example of a directed, now we said you could use matrices, of course, to represent directed graphs as well. But here is an example. This graph here is a directed graph. طبعا what you want to do is list the vertices in the row above the matrix and in the column in the correct order. And now, because this is a directed graph, you need to start with the column. Anytime you have a vertex, anytime you have an edge, directed edge from a vertex, in the column with a vertex in the row, you record 1. طبعا if there is no vertex, if there is no directed edge from the vertex in the column that goes to a vertex in the row, then you record 0. For example, for this graph, for V1, there is an edge starting at V1 going to V2. For V1 with V2, you record 1. There is another edge starts at V1 and ends at V5, so there is a 1 at V5. And I think I missed V4. There is an edge V1, V4, so you list 1 here. طبعا the remaining entries are zeros. Then there is no edge that starts at V1 and goes to V1, for example, or there is no edge from V1 to V3, so we record 0. So you do this for every edge in the column. Check every vertex in the row. If there is a directed edge, record 1. If there is no directed edge, you list 0. طبعا in this case you will get a 0 and 1 matrix. It will be a square matrix, but in this case it will not be symmetric. Then there could be a vertex, for example, from V1 to V2, but no there is an edge starting at V1 and ends at V2, but there is no edge that starts at V2 and ends at V1. But this matrix will not be symmetric. The next type of a different way to represent a directed edge is using incidence matrices. طبعا incident, if you recall, was used for edges. We say an edge is incident with a vertex. The incident matrices will use edges. For here in the graph, the edges must be labeled because they're used in the incidence matrix. So here is an example of an undirected graph. طبعا the vertices are labeled. In this case, numbers are used for labels. So the vertices are 1, 2, 3, 4. The edges must also be labeled. For E1 مثلا is the edge connecting 1 and 2. E2 is the edge connecting 1 and 3. E3 is the edge connecting 2 and 3. Finally, E4 is the edge that connects 2 and 4. For the way to do this now, the edges, طبعا the edges which are labeled, the labels for the edges is listed in the row above the matrix. E1, E2, E3, E4. In the column, you must list the labels for the vertices. In this case, it is 1, 2, 3, 4, 5. Now you form the column, each edge will have its own column. What you do is now for each edge, if it is incident with a vertex, you record 1. Like for E1 is incident with 1 and 2, we record 1 in both of these locations and zeros everywhere else. E2 is incident with 1 and 3, for list 1 with E2 with 1 is 1, E2 with 3 is also 1, the remaining entries are zeros. E3, for example, connects 2 and 3, so you have 1 with 2 and 1 with 3, and zeros everywhere else. Finally, E4 connects 2 and 4, so in the second entry in this column, you list 1, and E4 with 2, you list 1, and also E4 with 4 is also 1, the remaining entries are zeros. So this tells you, this graph is called an incident matrix because all the edges are labeled and listed, and the columns will tell you which vertices are incident with each of these edges. This is called an incident matrix. There is more examples of incident matrices. طبعا here this is a more complicated graph, but this is a graph. By the way, طبعا the number of edges will determine the number of columns, and each edge will have its own column. The number of vertices will determine the row number, the number number of rows in the column. Here is a graph that appears to have how many edges? It has 6 edges, but there should be 6 columns. There's also 5 vertices, V1 through V5, and there's 5 rows. فطبعا يعني for example, we'll just do one of them. E1, the first column, is for the edge E1. It seems to connect V1 with V4. يعني it's done the same way. This is the incident matrix for this graph. Here is one that has multiple edges. For example, the second example, notice E2 and E3 are multiple edges. They connect V1 with V2. So E2 and E3 will have identical columns, and they're incident with the same vertices. If you look at the second column and the third column, they are identical because the second column represents E2, the third column represents E3. They connect the same 2 vertices, but they are identical. Also, an interesting thing that's in this graph is a loop. If an edge connects 2 different vertices, there will be ones, and in each column, the one is repeated twice. But an edge representing a loop, one is repeated only one time. لأن a loop connects a vertex with itself. Look at the last column in this matrix. You will see one, and this column has only one entry that has 1. That is, this corresponds to the 4th vertex. لأن it only a loop is incident with only one vertex. In this case, it is V1. There's actually more than one loop. I was looking at the loop E8, which connects V4 with itself. Seems E1 is also a loop. If you look at the first column, it has 1 repeated only one time in the first entry. Then it's a loop incident with V1. Just like we did with the adjacency matrix, and if you know the matrix, you can reconstruct the graph from the matrix. The same thing for incident matrices. And if you have the incident matrix for a graph, you can reconstruct it. طبعا here is the graph, for example. Each column represents a different edge. If I start by doing labels, the first column is E1, then E2, E3, E4, E5. The rows represent edges, vertices. You can use labels A, B, C, D for labels. And طبعا the edges, since you have 5 columns, you have 5 edges, E1, E2, E3, E4, E5. Now use the matrix to construct the graph. Start by drawing vertices and label them, and then the edges will tell you which vertices are connected. For example, after you label the vertices, if you look at the first column represents E1. E1 connects D, the third vertex, which is C, with the 4th vertex, which is D. So you draw an edge between C and D. For example, E2, the second column, seems to connect A and B. You can connect A with B and label the edge as E2. Then go to through each column, and it will tell you which vertices are connected. You draw that edge and label the edge. But the result طبعا will give you the matrix. You started with the incident matrix and constructed the matrix from constructed the graph from the matrix. The final topic we'll cover is connectivity, what it means for a graph to be connected or disconnected. First, we have to define what a path is. In an undirected graph, what is a path? A path of length n, طبعا the length of the path is how many edges it uses. A path of length n from a vertex u to a vertex v is a sequence of adjacent edges going from vertex u to vertex v, and we will see what we mean, give examples of paths. So with a path you start at a vertex and ends with another vertex, and طبعا the length of the path is the number of edges you need. The vertices you list in the path has to be adjacent, and the length of the path is the number of edges you use. A path is called a circuit if it starts and ends in the same place. The u and v are the same. طبعا a path will go through every vertex on that path, so a path traverses the vertices along it. A path is simple if it contains no edge more than once. You cannot use the same edge more than once in the path. In this case it's called a simple path. Let's look at examples. Here is a graph. For example, an example of a simple path A, D, C, F, E. طبعا for this to be a path, there has to be an edge from A to D, an edge from D to C, an edge from C to F, and an edge from F to E, which there is. But this is a path that starts at A, and then we go to D, and then we go to C, and then to F, and end with E. But this is a path from A to E. طبعا it uses 4 edges, so the length of the path is equal to 4. Here is a circuit starting with B, from B to C, from C to F, from F to E, and then from E back to B. So this is a path that starts and ends at the same place, so it's a circuit. طبعا we used 4 edges, so it's a circuit of length 4. Not a path, an example of a sequence of vertices that do not represent a path is D, E, C, A, because there is no edge, there is no edge from E to C. Since EC is not an edge, then this is not a path. Not a simple path. This is certainly is a path. A, B, E, D, A, B. طبعا A, B is used twice. فهير طبعا the length, this is still a path of length 5 لأنه used 5 edges, but since AB was used twice, this is not a simple path. In a directed graph, a path is more difficult than you have to worry about the direction, but it's still it's similar to the definition of in an undirected graph, but the path must go in the direction of the arrow. You still have to be able to go from one vertex to the next, but you have to go in the correct direction. You have to follow the direction of the arrow. Here's a directed path. For example, if you want to start at A and end with C, you can go from A to D and then from D to C. A, D, C is a directed path from A to C. But there is no path that starts at C and goes anywhere. And there is no edges that start at C. A path in the directed graph, remember, you have to worry about the direction. You have to follow the direction of the arrow. Next, we would like to discuss connectivity. In an undirected graph, we say that the graph is connected if there is a path between every pair of distinct vertices of the graph. There is a path, any 2 distinct vertices, there has to be a path connecting them. The graph on the left is an example of a connected graph, while the graph on the right is not connected. For example, you cannot get from B to E. There is no path between B and E, but the graph is not connected. G1, which is to the graph to the left, is connected. G2, the graph on the right, is not connected. The graph, even if it's not connected, it will be it will consist of parts or components. Each component can be thought of as a connected subgraph. A graph that's not connected is a union of two or more connected subgraphs with no vertices in common. These disjoint connected subgraphs are called the components of the graph. Here is an example in the slide. طبعا we are looking at this all of this as one graph. Certainly is not a connected graph, but it's made up of three pieces. It's made up of three connected components, H1, H2, and H3. Each of these components is a connected subgraph. طبعا our graph is just a union of those three parts. Now the idea of connectedness with the directed graph, there's actually two conditions. There's a stronger condition. If satisfied, then we say the graph is strongly connected. If the graph is not strongly connected, it may satisfy a weaker condition, and it will be called weakly connected. So let's start with definition 1. A directed graph is said to be strongly connected if there is a path from A to B and from B to A whenever A and B are vertices in the graph. Remember now, these have to be directed paths. You need to be able to get from A to B and back from B back to A. That is a strong condition طبعا if it's satisfied the graph is strongly connected, and this has to be true for all A, B in the vertex set. طبعا a graph may not meet that condition, so there is a weaker condition. Definition 2, a directed graph is said to be weakly connected if there is a path between every two vertices when the direction of edges are disregarded. طبعا of course if you have a directed graph and remove the direction, you end up with a regular graph. If the resulting graph, if you remove the direction, if the resulting graph is connected, there is a path between any two vertices, then the original graph will be called weakly connected. Here is an example. The graph to the left is strongly connected. If we take any two vertices, there is a path going both ways. For example, if we take A and D, there is a directed path from A to D, and there is a directed path from D to A. Between any two vertices, there is a path that goes both ways. The graph to the left is strongly connected. The graph on the right is not strongly connected. There is no path that starts at A that goes anywhere. And if you, example, take A and D, there's a directed path from D to A, but there is no directed path from A to D. But the graph is not strongly connected. But if you remove the direction, you end up with a connected graph. There is a path between any two vertices. The graph to the right now is weakly connected.